Madam Sir, first of all, I would like to thank you for giving your time. My presentation is about the application of MXenes in tribology prepared by me, Oussama Zaidi, and Oussama Kharfan, two PhD students at Mechanical Department, Faculty of Construction Engineering, Mouloud Maamri Tizi Ouzou University, and Mr. Nishish Mustafa, Senior Lecturer at the same university. My presentation is based on this outline. Firstly, Mike's phases presentation. Secondly, MXenes synthesis methods. Thirdly, MXenes structures, then their properties, application, and their application in tribology. Finally, a conclusion is given. Mixed phases are generally a series of ternary layered compounds with a general formula Mn plus 1 IXN with n equal to 1, 2, or 3, in which M is a transition metal, I is an element of I groups in the periodic table, and X is carbon or nitrogen. These phases have a hexagonal structure, spaces group P6 3 over MMC, where the layers M and I are intercalated. The X atoms are located into the octahedral sets formed by M elements. There are more than 70 known mixed phases, and new ones have been constantly discovered. For example, the quaternary ordered mixed phases and similar materials such as the MAP phases. The distinctive properties derived from the usual combination of ceramics and metallic behaviors attract great interest. As a consequence, mixed phases are promising material for high temperature structure application, heating elements, rotating electrical contacts and bearings, and wear and corrosion protection materials. Mixed phases present strong bonds, preventing their cleavage through shearing or other mechanical methods. Therefore, for the first time, chemical exfoliation approach made possible the synthesis of 2D materials MXenes from primary mixed phases. The MX and MA totally strong bonds in the mixed phases can hardly be broken to make MXenes through a mechanical exfoliation method similar to that of graphene. The MA bonds can be broken and the A element layers can be removed by employing strong etching like hydrofluoric acids or lithium fluoride hydrochloric acid mixture or ammonium hydrogen bifluoride, resulting in multi-layered MXene with a general formula Mn plus 1 XNTX with n equal to 1, 2, or 3, where Tx are surface termination functionalities. The suffix n in MXenes presents the similitude with graphene as for morphological, electrical, and mechanical properties. Etching methods have been improved over the years, from initially dangerous HF etching to safe electrochemical etching. The difference in surface termination caused by the different etchant used affect the structure, electronic, and chemical properties. HF solution as an etchant used to synthesize many MXenes such as Ti3C2 TX, NB2CTX, V2CTX, and TE3CNTX. The proposed etching process for IL-based mix could be expressed as the following equation. The metallic MA bonds broke first. They are much weaker compared to MX bonds, and F and IL ions forms IL-F3 with the release of H2. In this way, the Al layer was pulled out of max little by little. The MA bound energy in nitride MXenes can be almost the same as or slightly higher than that of the MX bound, making the latter unsuitable for the matter wet chemical etching methods. Recently, molten salt etching has become a new method which is designed for nitride MXene members. This method is much more complicated than the wet chemistry. Computational simulators are extensively used to understand MXenes structure and to put out new possible stable compounds, aiding experimental development. Through these studies, it has been indicated that MXenes can be found in 6 possible structures. Mono-M elements, for example Te2C and Nb4C3, solid solutions such as TeV3C2 and CrV3C2 ordered out of plane double M elements in which one transition metal occupies the external layers, usually chromium and molybdenum, while the central ones are filled by another metal, for example, MXN, MO2TeC2, and MO2Te2C3. Ordered in plane double M elements, wherein the different M elements are ordered in the basal plane, such as molybdenum 2/3, yttrium 1/3, the all index to ILC. Vacancies ordered, for example, tungsten 1 and 3 and 3300s CTX, and vacancies randomly distributed NB1 and 3300s CTX. Schematic representation of MXN selected are shown in this figure. Among the unique MXN properties, high Young modulus, thermal and electrical conductivity, and the adjustable band gap are remarkable. Noteworthy, the hydrophilic surface with high metallic conductivity of MXNs distinguish themselves from the majority of 2D materials, including graphene. The main property of MXN family are electronic and electric, which can be tuned by functional groups alternation, stoichiometry, or solid solution formation. This figure presents experimental values of electrical conductivity of different compounds. In addition, it was observed that resistivity values increase with the number of layers and the presence of functional groups. Because of this, the simulated conductivities have generally larger values than the ones observed experimentally. Mechanical, as the MC and MN are among the strongest bonds, mechanical property of MXNs also attracted the great interest. The first simulation study has suggested elastic constants C11 at least 2 times greater than Meigs phases and other 2D materials. However, despite the C11 values 2 to 4 times lower if compared to graphene, their bending stiffness is higher, which point towards their use as reinforcement in composites. In addition, due to the functional groups, MXN have better interaction with polymeric matrices than graphene for composite application. MXN's versatility are attractive to several applications. Their high Young modulus, good electrical conductivity, and surface chemistry alteration appeal to composites, while chemical stability, ion intercalation, and adjustable band gaps point towards catalysis and energy storage applications such as fuel cells, hydrogen storage, and lithium batteries. Promising results were achieved in completely diverse areas, from optospectronics and flexible wearable electronic devices to environmental and biomedical ones. The latter received the majority of study since it is essential for clean and renewable energy generation and used in electronic systems such as electric vehicles. Recently, MXNs are applied in the field of tribology, the study of interacting surfaces in relative motion, in special friction, and will received increased attention since the Pioneer Jost report in 1966 due to its significant impact on the efficiencies of mechanical systems and the economy of several countries. It is estimated that 1/3 of the world's energy resources are used to overcome frictional processes. Transportation researchers indicated that tribological efficiencies improvements could reduce 500 million tons of CO2 emission in 10 years. In order to reduce friction and wear of different applications, from gears to medical implants for joint replacement, layered material like graphite, MOS2, and hexagonal bond nitride have been used. MXNs present several important features to tribology, such as high surface area, graphene-like morphology, and excellent mechanical properties. In addition, Meigs phases also presented promoting tribological properties in lubricating oil, even better than graphite. The MXenes tribological research has been restricted only to Te3C2TX and Te2CTX compounds. Therefore, it is imperative the study of other MXenes in this field. In this application, MXenes were incorporated to oil or polymer matrices. In the former, Te3C2TX addition enhanced the oil lubricant properties, significantly reducing the coefficient of friction as can be seen in this figure. This was attributed to the tribofilm formation, which provides the direct contact between the two rotating surfaces and also bear the indentar load due to the MXenes good mechanical properties. In this research, it was indicated that higher MXenes exfoliation degree results in lower COF and wear, as previously observed with graphene. The author proposed that the monolayers assist in the tribofilm formation, protecting the surfaces from direct contact. Finally, the addition of other nanomaterials such as TeO2 and potassium titanate may further optimize friction and wear properties. Despite the application of MXenes as base oil additive to our knowledge, only few studies as solid lubricant were realized in MXenes-based composites, and these topics remain relatively unexplored. The addition on the ultra-higher molecular weight polyethylene and epoxy resulted in enhanced wear resistance and lower COF values compared with pure matrices, as presented in this figure. The enhancement of wear resistance and COF reduction was attributed respectively to improvements of the composite mechanical properties, which results in better plowing and scratching resistant, and also the turbofilm formation, which results in lower contact area for plastic for deformation between the composite and the counterbody. After 11 years of their discovering, remarkable progress has been made upon MXenes synthesis structures and several promising applications with constant discoveries of new compounds. However, several challenges must be overcome to promote further development. Regarding their synthesis, there are three main barriers. The first is to extend the MXenes family. Up to now, only around an eighth of the mix phases were experimentally exfoliated, and 37 more are predicted to be possible. This is mainly derived from the limited production of nitrate compounds and the restricted synthesis procedures of mix phases with aluminum. Finally, the MXenes synthesis routes may be applied to similar materials, such as the MAB phases, discovering new 2D nanomaterials with novel properties. The number of theoretical studies are much greater than experimental ones, and several topics still need to be addressed. For instance, some properties were obtained through simulation and not experimentally confirmed. Finally, consider their industrial application. Two main aspects hinder MXenes practical use: high cost and structural properties instability. The former is influenced by the high cost of mix phases precursor plus MXenes synthesis delamination and manufacturing prices. Those cheaper synthesis procedures must be pursued, including the mix phases precursor and product manufacturing. Thank you for your attention.